Learning objectives. In this chapter, the user would learn the following in detail: solution of linear systems direct method, matrix inversion method, Gaussian elimination method, method of factorization, iterative method, Gauss-Seidel method. Statistical inference. Gaussian elimination pictures not used, pivot elements, updated elements. Definition. Forward Gauss elimination method. Gauss elimination method of solving a linear system consisting of equations in unknowns by bringing the augmented matrix Ax equal to B, where A comma B equal to A11, A12 etc. A1n and then B1. Similarly, we have tried A21, A22 etc. till B2. Then AM1, AM2 etc. AMN, BM. To an upper triangular form, this elimination process is also called the forward elimination method. 5x1 minus x2 minus 2x3 equal to 142 is called equation 1. x1 minus 3x2 minus x3 equal to minus 30 is called equation 2. 2x1 minus x2 minus 3x3 equal to minus 5 is called equation 3. Eliminate the term x1 from equation 1 and 2. Equation 1 implies 5x1 minus x2 minus 2x3 equal to 142. Then we have to multiply our equation 2 by minus 5. After multiplying by minus 5, we getting minus 5x1 plus 15x2 plus 5x3 equal to 150. After eliminating the term x1, we getting the equation 14x2 plus 3x3 equal to 292. It's called equation 4. Again eliminate the term x1 from equation 2 and 3. Equation 3 implies 2x1 minus x2 minus 3x3 equal to minus 5. Equation 2 into minus 2 implies minus 2x1 plus 6x2 plus 2x3 equal to 60. After eliminating the term x1, we getting 5x2 minus x3 equal to 55. Is called equation number 5. Using equation 4 and 5, we will get x2 and x3. After solving equation 4 and 5, we getting x2 equal to 457 divided by 29. Using this x2 equal to 457 by 29 in equation number 5, we getting x3 equal to 690 divided by 29. That is called 690 by 29. Using the values of x2 and x3 in equation 1, we getting x1 equal to 5955 divided by 29. Method of factorization. Given a number n, Fermat's factorization methods look for integers x and y such that n equal to x square minus y square, then n equal to x minus y into x plus y is called equation 1, and n is factored. A modified form of this observation leads to Dixon's factorization method and the quadratic sieve. Every positive odd integer can be represented in the form n equal to x square minus y square by writing n equal to ab with a greater than b, and nothing that this gives a equal to x plus y is called equation 2, b equal to x minus y is called equation 3. Adding and subtracting a plus b equal to 2x is called equation 4. Then a minus b equal to 2y is called equation 5. So solving for x and y gives x equal to a plus b by 2 is called equation 6. Y equal to a minus b by 2 is called equation number 7. Therefore, x square minus y square equal to 1 by 4 times of a plus b whole square minus of a minus b whole square equal to ab. As the first trial for x, try x1 equal to root of n, where x is the ceiling function. Then check if delta x1 equal to x1 square plus n is called equation number 9. It's a square number. There are only 22 combinations of the last 2 digits which a square number can assume. So most combinations can be eliminated. If it's not a square number, then try x2 equal to x1 plus 1 is called equation number Gaussian elimination method. So delta x2 equal to x2 square minus n is called equation number 11. Then x1 plus 1 whole square minus n is called equation number 12. x1 square plus 2x1 plus 1 minus n is called equation number 13. Delta x1 plus 2x1 plus 1 is called equation 14. Continue with delta x3 equal to x3 square minus n is called equation number 15. Then x2 plus 1 whole square minus n is called equation number 16. x2 square plus 2x2 plus 1 minus n is called equation number 17. Delta x2 plus 2x2 plus 1 is called equation number 18. Then delta x2 plus 2x1 plus 3 is called equation number 19. Gauss-Seidel method. Gauss elimination method is the direct method of solving the system of linear equations. The Gauss-Seidel method, called Seidel's method by Jeffries and Jeffries 1988 p.305, is a technique for solving the equations of the linear system of equations one at a time in sequence, and uses previously computed results as soon as they are available. Then xi power k equal to bi minus summation j less than I aij xj power k minus summation j greater than I aij xj power k minus 1 divided by aii. There are two important characteristics of the Gauss-Seidel method should be noted. Firstly, the computations appear to be the serial. Since each component of the new iterate depends upon all previously computed components, the updates cannot be done simultaneously as in the Jacobi method. Secondly, the new iterate x of k depends upon the order in which the equations are examined. If this ordering is changed, the components of the new iterates and not just their order will also change. In terms of matrices, the definition of the Gauss-Seidel method can be expressed as x power k equal to d minus l whole power minus 1, then ux power k minus 1 plus b, where the matrices d, minus l and minus u represent the diagonal, strictly lower triangular and strictly upper triangular parts of A, respectively. The Gauss-Seidel method is applicable to strictly diagonally dominant or symmetric positive definite matrices. Solve the following equation using Gauss-Seidel method. 9x plus 2y plus 4z equal to 20, x plus 10y plus 4z equal to 6, 2x plus 4y plus 10z equal to minus 15. Solution. Obviously, the largest coefficients occur along the diagonal, hence we can apply Gauss-Seidel method. The given equations are written as x equal to 1 by 9 into 20 minus 2y minus 4z, y is equal to 1 by 10 into 6 minus x minus 4z, then z is equal to 1 by 10 into minus 15 minus x plus 4zy. First iteration, putting y equal to 0, z equal to 0 in the first equation, then x power 1 equal to 20 by 9 equal to 2.22, then y power 1 equal to 0.38. Finally, z power 1 equal to minus 1.79 is obtained by substituting the values of x power 1, then y power 1. X power 1 is obtained by substituting the value y equal to z equal to 0. Then y power 1 is obtained by substituting the values x power 1, then z equal to 0. We getting the values. X power 1 equal to 2.22, y power 1 is equal to 0.38, z power 1 equal to minus 1.79. Second iteration, x power 2 equal to 1 by 9 times of 20 minus y power 1 minus 4z or 1. Then the final answer is 2.93. Then y power 2 equal to 1.02, z power 2 equal to minus 1.68. Finally, we getting x power 2 equal to 2.93, y power 2 equal to 1.02, z power 2 equal to minus 1.68. Third iteration, x power 3 equal to 1 by 10 times of 20 minus 2y power 2 minus 4z power 2. We getting the answer 2.74. Then y power 3 equal to 0.998, z power 3 equal to minus 1.648. Finally, we getting x power 3 equal to 2.74, y power 3 equal to 0.998, z power 3 equal to minus 1.648. Fourth iteration, x power 4 equal to 1 by 9 times of 20 minus 2 into 0.998 minus 1.648. The final answer is 2.73. Y power 4 equal to, we getting 0.986. Then z power 4 equal to, substituting the values of x power 4, then y power 4, we getting the answer minus 1.645. The final answer is x power 4 is equal to 2.73, y power 4 is equal to 0.986, z power 4 equal to minus 1.65. Fifth iteration, x power 5 equal to 1 by 9 times of 20 minus 2y power 4 minus 4z power 4. We getting the answer 2.74. Then y power 5 equal to 0.98. Then z power 5 equal to minus 1.66 is obtained by substituting the values of x power 5 and y power 5. We getting minus 1.66. Then the final answer is x power 5 equal to 2.74, y power 5 equal to 0.98, z power 5 equal to minus 1.66. Sixth iteration, x power 6 equal to 1 by 9 times of 20 minus 2 into y power 6 minus 4 into z power 6. We getting the answer 2.74. Then y power 6 equal to 0.99. Then z power 6 equal to minus 1.65. The values at the end of the fifth and sixth iterations are almost equal. The required solutions are x equal to 2.74, y equal to 0.99, then z equal to minus 1.65 approximately. Conclusion. In this chapter, we have covered the following in detail. Solution of linear systems, direct method, matrix inversion method, Gaussian elimination method, method of factorization, iterative method, Gauss-Seidel method.